So here's a challenge for you. How about the integral of 1 to infinity 1 over x cubed minus 0.1 dx? I graphed it for you. Really, they all look like this. So I just kind of sketched what they all look like. So can you use a p-test on it? If you can't, what else can you do? So can you use a horizontal p-test? Well, you can't use it exactly because it's not exactly 1 over x to the p. So you can't use it directly. Can you do a direct comparison test? With what would be the obvious thing to do it with? 1 over x cubed. So how does 1 over x cubed minus 0.1 compare to 1 over x cubed? Here the denominator for x greater than 1, the denominator here is smaller than the denominator here, so the fraction here is bigger than the fraction here. So if I was to draw 1 over x cubed, it would actually be smaller than the function we have here. So I'm drawing it in red because it's a lower bound. And then what? This integral is convergent, right? Since p equals 3 is greater than 1 is the cutoff for a horizontal p-test. So this integral is larger than a convergent integral, which tells us nothing. Maybe it's so much larger it's infinity. We don't know. So no conclusion from that direct comparison. Being larger than a finite number doesn't guarantee that the integral is finite. So what other ways could we reason about this? Take a few minutes to think about it. Well, there's a few good ways. You could say that x cubed minus 0.1 is really, really close to x cubed, right? If x is large. Like if x is 10, then 10 cubed minus 0.1 would be 1,000 minus 0.1, which is pretty darn close to 1,000. So you might say, in the long run, as x goes to infinity, that 0.1 just doesn't matter, right? What's really important is how fast x cubed is growing. So we could actually say that x cubed dominates the behavior of all the other terms here. So what we're saying is 1 over x cubed minus 0.1 is basically one over x cubed as x goes to infinity. That's sound reasoning. I know it might sound a little iffy, but we can prove it rigorously by like dividing top and bottom by x cubed if we really want to. So what I would call this is an informal p-test. I'd say the integral 1 to infinity 1 over x cubed minus 0.1 converges, since the integral is basically integral 1 to infinity 1 over x cubed dx, which has p equals 3, which is bigger than 1, so the integral converges. So I would say that's an informal p-test. It's perfectly good reasoning. As long as we don't have like exponentials in there, like e to the x, as long as it's all powers, we're pretty good. You can still do stuff like that with exponentials, but you have to be more careful. So that's an informal p-test. You can also do informal p-test to prove divergence if you had like 1 over root x plus some other terms that didn't dominate the root x, then you could use the same argument. A more formal version you could say, let's compare 1 over x cubed minus 0.1 with 1 over x cubed. So we're going to take the ratio of those. What do you think that ratio does as x goes to infinity? So we're going to take the limit as x goes to infinity. So we said those are basically the same number, so that equals 1. So there's something called the limit comparison test, which says if you take that ratio, take the limit as x goes to infinity, if you get any finite number here, then either both integrals converge or both integrals diverge. So if the limit of that ratio, which we could call f of x over some g of x, f of x is our original integrand, g of x is some hopefully simpler thing that we're thinking of where we know how that integral behaves. So if that integral exists and is bigger than 0, then the integral, we'll just say 1 to infinity, you can make it a little more general. So then that integral behaves like integral 1 to infinity g of x. Either both converge or both diverge. So you'd want to pick a function here where you know whether the integral converges. We know the integral of this converges. Since this limit exists and is bigger than 0, we know that the original integral also converges because we know that this one converges. So that's the limit comparison test. The book expresses it in more formal language, which is nice. So you can go read about that.